Thank you so much. So my name is Tenglong Li. So this is work I have done with my collaborator, Professor Laura Wright at Boston University. So we talked about a little bit about how to build TB models for TB household contact study. So a little bit background, right? So TB and the pathogens that cause TB, and TB is known to be one of the oldest infectious disease, and yet it still remains a major threat to global health. Actually, annually, I think there's every year there's about 10 million new cases coming up. Also, TB annually can cost about more than 1 million deaths. So you can see how deadly TB can be. And the pathogen that cause TB is called Mycobacterium tuberculosis, which features long latency, and the latency could be months to even 2 years. Also, the TB can have imperfect diagnostic, who have low sensitivity and low specificity. And the factors which from TB infection lead to TB disease, and which the process known as progression, the factor of progression, still largely unknown. And also, there's a phenomenon called multiple drug resistance in TB. Basically, the TB patients are unreacted to therapies and to the common drugs. Also, the TB global control is largely disrupted by COVID, and this is unfortunate thing because most manpower resources have been migrated to COVID control and prevention, and now the notification rate of TB get lower and lower. Also, TB controls in China, where I live, still China is considered as a high burden country in all the 3 categories set up by WTO, which is high burden in cases, also in HIV, TB, also in, I think, MDR, the multiple drug resistance. So specifically talk about TB household contact study, right? So the design is really start with so-called index case. The index case refers to the TB cases. So, they are confirmed in lab by smear and culture test results, and they're really sick. Usually they seek healthcare by visiting local clinics, and they follow up with TB control agencies. And they're usually adults having usually more than 2 or 3 household contacts in order to establish plausible household transmission sources, and then the follow up with household contacts. Those who have frequent and non-trivial contact with index case, so we know there's really a household transmission ongoing. And after that, so the study researcher are going to collect information from the index case, from their household contacts, as well as their living environments for example, like if their household is crowded, or how many windows their household has. So the main application of this is really because for this kind of design, really have a plausible household transmission, and we have source identified. So it's really convenient for TB researcher to learn how MTB as a pathogen of TB transmitted across different household members. So this is actually a so-called random directive graph model. So it's really originated from the flu. So it's first applied in influenza. And here is an example of such graph, right? So for example, there's a household with four members, and subject 1, subject 2, they're infected, which subject 3 have unknown infection status. And because subject 1, subject 2, they're infected, so they should receive so-called edges, which basically represent transmission passes. And subject 3 is unknown, so it can be either infected or not infected. So it have more flexibility for drawing edges to each subject 3. And subject 4 is not infected, so he or she should never receive any edges from anybody. And such graph usually is randomly drawn, except that you have to make sure such graph is consistent with the observed data, like the rules I just mentioned. And flu design, so which flu they have I think it have its own household contact study design. It's really good because they usually enroll household before so-called flu season, and after flu season ends, and they do the follow-ups and measure, for example, their infection status and so on and so forth. And this is actually, later I'm going to talk about this, is much better than the TB household contact study design, which usually, which become the focus of our project. So research goals, our goals usually have four. Many have four goals. The first is we trying to define rules for drawing random directed graph for MTB transmission. The second is we're trying to deal with issues that occurs, mainly in the TB modeling, in TB model parameter estimation. And the reason is because, first, as I said, TB design is different and inferior to flu design. And the major difference that, flu design, you see, is have this a really good cohort study, while TB design usually they only enroll household with the index case, who are known as the TB patients, right? So in order to establish such household transmission sources, but they don't really usually enroll so-called right nowadays called community controls, which refers to the household, don't have any TB cases, so that there's no household transmission going on in those community control household. And this is something like you do clinical trials, but you don't have control group. And on top of that, a lot of TB household contact studies, they don't really have good variable, good measurement. They are very predictable TB transmission. And because of those two issues, and the consequence is that when you build models, usually it's really hard to identify some baseline parameters. And as a result, it's really hard to use to draw certain graphs because we're going to use MCMC later on, you can see, and it's really hindering the so-called edge imputation in the process. And the third goal, of course, we're trying to design comprehensive MCMC algorithms that incorporates 1, 2 points. And the fourth, we're trying to discover some epidemiological implications based on some simulation. So the TB random direct graph, right? So here's an example. For example, this is household 4, and we have subject 1, 2, 3, 4. And for example, subject 1 who is a TB case, and he's diagnosed on July 1st, 2015, and he's have subject 2, and who is also a TB case diagnosed on March 1st, 2016. And subject 3 is latent TB infected, but not have disease. Subject 4 is not infected. So in that case, we suppose subject 1 is probably the earliest case. So in that case, we can only draw edge from 1 to 2, not vice versa. This is because based on the diagnostic date, we assume or we suppose there's a temporal order for the transmission chain. But of course, we also consider the possibility of reporting delays. For example, if subject 2 is diagnosed on August 1st or September 1st, basically within 3 months, that's kind of the threshold we set up. And we think there are co-prevalence cases, and the edges or the transmission passage can go either ways or can go both ways in the random directed graph. So we're trying to make a matrix presentation of the above random direct graph just to make sure things really sort out in a mathematical order. And the main thing is we're trying to define so-called edge parameters. And you see, based on the above matrix, we're trying to define A12, A22, A13 up to A33. So those A's, they sort of represent different edges. While where 1 represents the presence of edge and 0 represents absence of edge. And we're trying to, so the essence we're trying to do is we're trying to impute those missing parameters or missing values or the parameters along with estimating the transmission model parameters we're going to see in the next slide. So here is the first scenario, right? So we consider models when you have really good measurements or really powerful predictors of transmission. So here, the first line is really usually just a Bayesian model, right? So we have posterior distribution PG, which represent the graph, and theta is the model parameters. And the first component PY condition G and theta just to make sure it's just a function to make sure that your graph to draw is consistent with the observed data, while PG theta is really what's going on in the water, right? So what's the likelihood of your graph condition on the parameter of theta, and P theta is prior. So this likelihood PG condition theta, you should have 3 main components. The first component is you can see on the next slide, the PCI is called, basically refers to the probability of getting a community transmission, also called actual household transmission. It depends on, there's a baseline parameter alpha, and also depends on risk factors. For example, your individual feature xi, also the community feature xc. And the last component, the second component actually refers to probability of getting household transmission. It depends on, for example, household features, XH, also individual feature XI, also, the infectee feature XI, also the infector feature XJ. And here is really important. We point out that the alpha, which we highlighted in red, refers to baseline risk. And here we assume the baseline parameter in the household and in the community transmission model, they're the same. Just mainly because you include enough powerful controls so that this assumption becomes plausible. But I think more often that in TB household context study, you don't have powerful controls. You only have some limited measurement with measurement errors. So in this case, with the same model, you cannot write the baseline parameters in community transmission PCI as equals to the baseline parameter in the household transmission as alpha. So in that case, we write alpha C represent for each baseline risk for each community, while alpha keep its own way as the baseline for the household transmission. So we now really focus on the worst scenario, right? So what if you have only limited model controls and you don't have community controls? So that means you have bad measurements or limited variables and you don't have the good design, which is a typical TB household context study design. The solution is to transform this into a Bayesian prior selection problem. And so basically what we're trying to do is for each edge parameter, as I showed you earlier, so we're trying to build an informative prior for the parameter to guide the imputation of household transmission passes. And what we do is we basically use the DIC to compare like multiple different priors. And eventually, I think we're going to be able to select priors and fit the observed data well. And we choose those priors and we'll then see how the result can look like. So what I do is trying to make things a little bit simplified, right? So here is how I define the prior probability for household transmission path to happen, which is an inverse logic function, right? So inverse logic function of W. So W here serves as a hypertuning parameter. So and I define 1 minus P as community transmission path. So I only need one W to control the prior and control the different priors for different parameters. So basically we select different values of W that lead to distinct posterior samples. And we only can, so one comment is we only can approximately compute the IC because, so what the likelihood really depends on on the random dialectic graph, which cannot be seen, which happen under the water. So basically what we do is using sort of a simulation to approximately compute the DIC. So finally, we be able to select different posterior samples based on their priors and according to the DIC. So we do 2 simulation studies. So first study, we have model with rich controls, with a bunch of variables we think are really powerful, predictive of transmission. Second one, we have model with very limited controls, only 3 variables at our gender and crowding. So, and we have different scenarios to reflect, this may happen in, various kinds of regions, on the world. In the first simulation study, remember, so here is when you have powerful controls in the model and you have only basically one parameter for the baseline risk. In this case, we don't have any identification issue. You can tell that there's only minimal bias. And the simulation value, which represented by the red cross, is well inside the confidence intervals and pretty close to the median of posterior samples, which represent the black dots. And the coverage rates, at least here, all pretty close to the 95% nominal rate. So that's a good sign. So the second simulation study, right? So what I'm trying to do is, I get DIC and simulate data, for each of those 4 scenarios, and each scenario have maybe different kind of strengths of forces in terms of the actual household or community transmission and household transmission. So basically what I can tell is the DIC performed pretty well, and it's actually indeed can help in scenario 1, 2, and 4, but only struggle in scenario 3, where we have about 50 to 60% household transmission, and the other 30 to 40% is attributed to community transmission. So in that case, we think that probably the reason is because the signal is pretty blurred and not strong enough, and because of household transmission, so it's the household gonna have a lot of infections and very difficult for DIC to tell apart. So, and we also, based on simulation study 2, remember, so this is the case we don't have community controls and we only have a limited model controls. we compared estimation of baseline parameters because that's where we find the identification problem. So basically, we compare 3 different methods, right? So first method, you see I group 3 different estimation, into a cluster. So one on the left is where we don't really use any DIC, right? So only use the original data with uninformed prior. And you can tell it doesn't really change much across 4 very different scenarios. So that's a sign of the appearance of or existence of identification problem. The one in the middle actually is when we use the DIC guided prior, based on the raw data, and you can tell it's help a lot, right? Especially for when you have strong community, strong extra host transmission, right? But it doesn't really come with any cost. It actually comes with a mild or modest cost of bias. Also, you actually precision get much worse because you intentionally increase your posterior sample or expand your posterior sample. And this is the result when we compare different risk factor estimates. So this is actually, for example, the effect of adults, the effect of crowding, and the effect of gender, female. And you can tell it's pretty, so all the risk factor effects, they are pretty consistent, and they are consistently unbiased across different scenarios. And the only thing that I think notable is the effect of crowding. And effect crowding actually, you see the confidence interval become much wider when you have predominant X household transmission. Basically, when the household transmission is very small, you're probably going to struggle with the precision for estimating the crowding. And the reason is because the crowding effect only associates with household transmission. So when household transmission is very minimal, it's getting overshadowed by the community transmission, you're probably going to struggle with identifying this particular effect because it only associates with this household transmission, not really associated with community transmission. The last one, we do the empirical example using a Brazilian household contact study, and we have 160 households, and we enrolled 934 household contacts. And the contact was screened and get their TST readings collected in order to make sure there's infection status, whether they're infected or not. And we only have 3 controls in the model as designed in the simulation 2 study. We have adult, which is who is age 18 or older, and gender and crowding. The crowding is based on the ratio between the number of inhabitants in the household and the total number of living rooms. So this is what the DIC plot tells us. So the DIC plot really tells us to select the posterior sample have prior that favors actual household transmission. So basically we select. So you see the threshold line we draw with the red dashed line. So we select all the 5 posterior samples that go below the threshold. So in total, we have a posterior sample of 550,000 different draws of parameters. And because I mentioned we have to simulate this epidemic in order to get a sense of what's going on for the transmission chain or the random directed graph. So we simulate epidemic for each of those 50,000 draws, and each simulation actually we simulated for 10,000 households, so to make sure it's a large scale. So in that case, we'll be able to get some key epidemiological insights. For example, the first one is we'll be able to estimate the proportion of infections attributed to household transmission. In this case, so only 5.6%, and the proportion of infection attributed to community transmission among household contacts was pretty large, was 83.7%. And such pattern is pretty consistent across 4 different municipalities. And for the risk factors, we find that being adults was nearly significant, while crowding is really not so significant, and the gender really doesn't really have any effects. And as I said before, the crowding, because crowding only associates with household transmission, so we have to be careful because in this case, household transmission indeed overshadowed by the community transmission. And this is the last slide. Basically summarize the whole process of our statistical framework for building a random diagram model in a TB household contact study. So thank you so much. So that'll be all.
Thank you very much, Tenglong. So now we'll open up for any questions. And as a reminder, if you'd like to ask a question, you can raise your hand. If you see the reactions icon at the bottom of your Zoom screen, if you click the little up arrow, there's a raise hand function there, or you're also welcome to use the chat function. Give people a couple of minutes to formulate their questions. I'm not seeing any immediate questions. Tenglong, I don't know if there's any other parts of your presentation that you wanted to delve into a little more deeply. We've got a few minutes to consider doing that while we
Sure.
wait.
I think what I can do is I can share the workflow chart, because I'm worried about I'm running out of time. So I can share my screen again. So this is the workflow. So I think this is basically just like an overview of all the work we have done. So this is the process we think, what people should do if they want to build a similar model, based on the TB household contact study. And I'm not sure if I have seen any questions.
Well, if there are no questions, we can end a little early. If anybody does have questions they'd like to ask Tenglong directly, you can contact him individually, and otherwise we can just end a little bit early and come back at 1 p.m. for the lightning talks.
Thank you so much.
Yes, thank you very much.